I'm Grace Richards, a first-year PhD student at the Open University, researching how to extract and analyse volatile organic compounds from Enceladus' surface ice. Enceladus is an icy moon orbiting around Saturn. It hosts a liquid water subsurface ocean and has evidence of hydrothermal activity. On Earth, life exists where there are organic compounds, liquid water, and an energy source. Enceladus meets all three of these requirements. Ideally, we'd like to find out more about what is in the ocean, but the icy crust is around 5 kilometres thick at the South Pole, and it is currently impossible, even on Earth, to drill to those depths. A compromise may be to look at the surface. Material from the ocean is ejected via the plumes, and the majority falls back onto the surface. Because of this, the surface can provide us with information about plume and oceanic composition, and therefore habitability. As Enceladus orbits Saturn, it is subject to space weathering processes, such as bombardment from high-energy electrons from Saturn's magnetosphere. It also sweeps up material from the E-ring, the second outermost ring of Saturn. These processes modify the surface of Enceladus. However, because of the amount of material ejected by the plumes, they are very difficult to detect. It is therefore important to investigate how the space environment affects the surface, as this is vital to extract the most information from samples and develop equipment best suited to Enceladus. Currently, the only firmly detected surface components are water and carbon dioxide, with ammonia and methanol expected. A lander mission would be able to tell us a lot more about Enceladus' composition. However, there are challenges to analysis, such as the low temperatures, pressures, and gravity. In my PhD, I'm developing new methods and extraction techniques which minimise these issues. The main goals are to grow ices representative of Enceladus, build instrumentation which accurately detects volatiles, and investigate the effects of space weathering. Gas chromatography mass spectrometry, GCMS, is considered to be the gold standard for analysing chemical and isotopic composition of samples, and has been integral to previous spacecraft payloads. In the lab, I'll be growing ices representative of Enceladus, using a cooling plate within a vacuum chamber. I will use liquid nitrogen to cool the system down to -95 degrees Celsius. Gases will be trickled into the chamber so that they freeze inside it, forming the ice. The vacuum chamber will be coupled to a GCMS, and I will investigate 2 different techniques to find the best way to extract the volatiles from the ice. Solid phase microextraction is used to increase the sensitivity for the analytes of interest, but there are issues with this method such as the fragility of the fibre. Another possibility is membrane inlet mass spectrometry. Gases are extracted across a semi-permeable hydrophobic membrane, eliminating issues with the high water content of the samples. In the later stages of my PhD, I'll be simulating the effects of space weathering. The effects of impact gardening will be tested using the all-axis light gas gun at the Open University. The idea is to use my ices as a target and fire powdery rock projectiles at them, simulating E-ring grains impacting the surface. Using my ices and bombarding them with a 1 kiloelectron-volt beam of electrons should also demonstrate how particles from the magnetosphere affect the surface. After investigating these processes, I'll be using the equipment I've developed to retest the ices and detect any changes in ice composition. This will ensure my equipment is best suited for a wide range of possibilities on the surface of Enceladus. The work I am doing aims to improve methods to analyse the composition of icy moon surfaces and will be used to develop instrumentation which will serve as a prototype for future payloads.